Let's see some examples using geometric series. To start, let's practice using some of those formulas we derived. If I want to find the sum of k equals 10 to 20, 3 times 1/4 to the k. First of all, notice that this is a finite sum. So I want to use that first finite sum formula we looked at. And that involved knowing several things. So we said that we would always multiply by the first term of the sum. The first term is when k is equal to 10. So that would be 3 over 4 raised to the 10th power. And we multiply that then by 1 minus r raised to the number of terms divided by 1 minus r. So I need to fill in the value of r. Notice here that the value of r is 1/4. So that goes in these two places. And in the top, I need to raise that 1/4 to the number of terms. And remember that to find the number of terms, we look at what's on the top and bottom. In general, you can take the number on the top, subtract the number on the bottom, and add 1 to find the number of terms. And in this case, that gives me 11. So this would be the sum of what we have in sigma notation. As I look at another example, if I want to look at the sum from k equals 100 to infinity of 1/2 to the k minus 2, there's a couple ways I could approach this. First of all, unlike example 1, because this is an infinite sum, if I'm going to use my formula to find the sum of this series, it very much matters that our r value in absolute value is less than 1. Otherwise, we couldn't find the sum of the series. We would say that it would diverge. So I see here that in this case, r is 1/2. So that works. A couple things to observe here. We're used to having our r value written to the k, but I could write this sum as 1/2 raised to the k times 1/2 to the minus 2. 1/2 to the minus 2 here, we could express as 2 squared, or 4. And then we would be able to write this in the following way. So we would take our first term of this series would be 1/2 raised to the 100th power times 1/2 to the minus 2, so times 4, all over 1 minus the r value. 1 minus r here is 1/2. So we could simplify this to 1/2 raised to the 100th power. And really I have a 2 squared in the numerator, and I'm dividing by a 1 over 2, so this would be times 2 cubed. So we could simplify this to 1/2 to the 97th. I'll point out though, this step we did here, where I broke this up, it wasn't really necessary. We could have instead simply noticed that this is geometric. The first term would be 1/2 to the 100 minus 2 over 1 minus 1/2. That's 1/2 to the 98th divided by 1/2. It's 1/2 to the 97th. So the key thing here is essentially that if I have a constant raised to k plus or minus a constant, so having that kind of 1k in front, that's going to be geometric, and we really wouldn't have to separate those terms in order to use the formula. You could actually use it in the current way it's written. And a third one here, what if we had to find the sum from 1 to infinity of 2 raised to the minus 2k times 1/3 to the k plus 1. So here, what we have to be careful with is that it looks like there's kind of 2 r values, but if I really suspect that this is geometric, I need to be able to simplify it such that I get one constant raised to something dependent on k. So we have to use some algebraic properties here. And I can go about this again in a number of ways. A couple things to note here. 2 to the minus 2k is the same thing as 2 to the minus 2 raised to the k. And that's the same thing as 1/4 to the k. And much like we talked about in the previous example, 1/3 to the k plus 1 is 1/3 to the k times 1/3 to the first power. So putting that all together, I can rewrite the terms of this sum now as 1/4 to the k times 1/3 to the k times 1/3. So now the advantage is we've gotten it closer so that I have two numbers, both raised to the same exponent, being multiplied together. So we're going to be able to combine this part as 1/4 times 1/3 raised to the k. So we're going to be able to simplify this now. I still have this 1/3 to the first power, but now it's multiplied by 1/12 to the k. And this looks much more like a regular geometric series. At this point, I can note that 1/12 is the absolute value of r. That's less than 1. So, whoops, that's worth kind of pointing out here. And therefore, I can apply my formula. I know that this series converges, and it's going to converge to the first term, which is 1/3 times 1/12 raised to the first power. And then this is divided by 1 minus 1/12. And here we have 1/3 times 1/12 over 11/12. And we can simplify that to 1/3 times 1/11th, or 1 over 33. So we can see that we want to be on the lookout for things that we believe are geometric, and part of our task is to figure out what r is, and it might not be immediately obvious. We might have to do some manipulation of the terms before we can get to that point. Now what I'd like to do, so that was a focus on a situation where we had all geometric series, but one thing that's going to be important and challenging as we go along here is trying to fold this into what we've already seen. So we're going to encounter series and want to be able to use any new information we're seeing, but still remember what we've already seen up to that point. So I'm going to look at several series here, and we'll say for each series, decide if it converges, if it diverges, or we don't, I should say currently, have enough information to decide. And I say currently because, again, we're going to continue to see different tests for convergence and divergence. So it could very much be the case that we don't have information at this point, but if you were to look back at this lecture after seeing some future ones, you would be able to determine that. So the first example is the sum from k equals 1 to infinity of arctangent of k. So at this point, we've talked about the definition of convergence. We've talked about the test for divergence, and now geometric series. So when I look at this, one thing that sticks out to me is I could simply take the limit of the terms of this series. And in fact, this isn't a bad thing to always try because it's quick to check as long as we don't use it mistakenly. So in this instance, the limit of the terms is pi over 2. That's significant in that it's not equal to 0. So we're able to say that the series diverges. And again, we want to get into the habit of justification, and this would be by the test for divergence. So you can always check the terms. Importantly, I want to stress again, if you ever get that the terms go to 0, you have to move on to a new test. That's going to be inconclusive. All right, our next example might look like the first one, but here we're going to have arctangent of k plus 1 minus the arctangent of k. Those are our terms of our series. And in this instance, the terms would go to pi halves minus pi halves, or 0. It's not geometric. So my hope is that I can use the definition of convergence. And one thing that stands out about this is that this is actually a telescoping sum. So we've seen those, and if you suspect that you have a telescoping sum, the goal is to find a pattern for the nth partial sum. So I have the first term would be arctangent of 2 minus arctangent of 1. The second sum, or the second partial sum, would be that first term plus the second term. And as soon as I get to the second term, we already encounter cancellation. I can see that this arctan 2 cancels with the first one. And I want to get to a point where I can observe my pattern so that I can observe that the nth partial sum will always have that minus arctan n that hasn't canceled, arctan 1. That's never going to cancel. And we would always have a positive arctangent term. And the connection here, if we look at when the subscript was 2, we had arctangent of 3. When the subscript was 1, we had arctangent of 2. So it looks like an n plus 1. By finding that pattern, I can now talk about the limit of the partial sums, which is equivalent to finding the limit of arctan n plus 1 minus arctan of 1. As we observed previously, the limit of that first term is going to approach pi over 2. The arctangent of 1 is pi over 4. So taking that difference, we get pi over 4. So importantly, we need to make a conclusion about whether or not this series converges. Because the limit exists and is finite, the series converges, and the justification here is by definition. And on top of that, we got the extra information, which wasn't asked for, that we can find the sum of this series is pi over 4. Now if I have the sum from k equals 1 to infinity of sine of k over k squared, if I start to think about what we've seen so far, that's not telescoping. So it doesn't seem that I would be able to come up with a nice pattern for the nth partial sum and use the definition. The terms of this series do in fact approach 0, so the test for divergence is inconclusive. And further, it's not a geometric series. It doesn't have terms that are a constant raised to the index. So considering everything we've seen so far, we don't have enough information to consider what would happen to this. And in particular, it won't be until we talk about the absolute convergence theorem in series with negative terms that we'll be able to come back and study something like this. And finally, if I have the sum from k equals 1 to infinity of root 2 to the k times 3 to the minus 2k plus 1. Here, this looks very complicated, but I'm thinking that this might be geometric because I see those constant bases raised to exponents that involve the index. So much like we saw in the last example of this first part, I want to try to simplify those terms. So off to the side, I might play around with that first. So we have square root of 2k times 3 to the minus 2k plus 1. So square root of 2 to the k, that's the same thing as the square root of 2 raised to the k. And if that's not clear, remember that you could think of that as 2 to the k to the 1/2, what was given there. And you can multiply those exponents and then separate them in a different order. So that's kind of the justification for why I can write that as square root of 2 raised to the k. And then I have times 3 to the minus 2k times 3 to the first power. So breaking that up further, 3 to the minus 2k is the same thing as 3 to the minus 2, or 1/9 raised to the k. And then this is times 3. And so I can put this all together. I have that constant of 3, and then the part raised to the k is the square root of 2 over 9. So this original series could have been expressed as 3 times square root of 2 over 9 raised to the k. Those are equivalent. The advantage here is I can see that this is geometric with the absolute value of r equal to the square root of 2 over 9. Square root of 2 is certainly less than 9, so this is less than 1. And I can say that the series therefore converges. And that's all that's asked here, so that suffices. But I'll point out that if we were asked, we could find the sum. So it converges, but moreover, it converges to, so if we bring up that series there, the first term, which would be 3 times root 2 over 9 to the first power, all over 1 minus root 2 over 9. So we could find the value of the sum of that series, but to be clear, we only, according to the instructions, had to decide if it converged or diverged. And so now we can see that we're kind of building up our tools and trying to decide what to use where for different series. And that takes practice and experience in deciding what is the appropriate tool. And as we proceed through the next several lectures, we'll continue to add to those tools.